Hi, I'm Jack Guilfoyle, and this is my short presentation summarizing my individual extension to the Kink Dynamics project. I studied how the initial collision speed controls interactions of kink and anti-kink collisions in the 5⁴ model. I'll explain the model and the numerical approach, show key diagnostics, and highlight the resonance windows and the fractal-like structure I observed. The 5⁴ model describes a scalar field, which I will call phi of x, t, with potential energy function u of phi equal to this. This model supports topological objects called kinks and antikinks, localized waves that connect the two vacua where phi equals +1 and phi equals -1. In simple terms, a kink looks approximately like a hyperbolic tangent, which we will write as tanh of x. In the simulation, I'll place a kink on the left and an anti-kink on the right and give them equal and opposite initial speed, which I will call v. Numerically, I discretize the interval from -L to +L using a uniform grid of endpoints. The second spatial derivative is approximated by a centered finite difference. Time integration uses MATLAB's 113 ODE solver, an adaptive variable step method. Typical parameters I used are n equals to 200 grid points, the half domain range of L being equal to 60, time step delta t equals 0.01, and the total time big T to 100. Initial conditions used are the analytic Lorentz-boosted kink and anti-kink, so the only parameter varied in the sweep is the initial speed v. The boundary conditions used are homogeneous Newman. To quantify collision outcomes, I used 3 key diagnostics. First is the bounce count. I monitor phi of 0, that is the field at the origin where the kinks collide, and count how many times it crosses below a certain arbitrarily chosen threshold value. Here I used the threshold phi equals -0.3. Each dip below and return above this threshold is counted as one bounce. Figure 1 here shows the bounce number as a function of initial speed v. You can see the wide capture at low speeds, single bounce escape at high speeds, and narrow resonance windows in between. Secondly, I visualize phi of 0 across time and initial speed as a color map. Long horizontal bands of persistent oscillation correspond to trapped bounce states, often called bions. Brighter, quickly decaying regions above the critical value of v equals about 0.23 correspond to rapid escapes. This color map makes resonance windows clearly visible as vertical bands in the speed direction under this critical speed value. Thirdly, I also measured final separation and outgoing speeds. So I locate the 2 main peaks in the energy density at each time, and I refine their positions using a small quadratic interpolation across 3 grid points, and then I average their separation in the final 20% of the simulated time. For outgoing speeds, I fit a straight line to the peak positions at later times, and then take the slope as the speed. Figure 3 here displays the outgoing speed estimates for the left-moving and the right-moving solitons, and also it shows the mean magnitude. We see that the 2 kinks are approximately symmetric, with only minor numerical errors. A very notable feature is the resonance windows themselves. Physically, these windows happen because kinetic energy from the kinks can be transferred into an internal vibration of the kink, which can be seen as internal waves. Later, if the phase is just right, the energy can be returned back to the motion, allowing the pair to escape after a further bounce. To further explore the fine structure of these resonance windows, I implemented a velocity zoom routine. The procedure is as follows. I start with a coarse velocity window, I compute the bounce number across that window, and then locate the region of largest variation. And then, as you can see, I zoom in and repeat this routine. Repeatedly doing it reveals narrow windows embedded within these windows, so one sees a fractal-like, self-similar structure. This also confirms that resonance windows persist down to very small scales, limited only by numerical resolution. Summarizing the main conclusions, we have a critical speed V-crit, which is roughly 0.23 to 0.26 depending on the parameters that we use. This separates bioinformation from the single bounce escapes. Below this threshold, the dynamics are dominated by resonance windows, where multiple bounces or even a capture occur. Narrow windows persist on smaller velocity scales, revealing complex fractal scattering behavior like we've seen before. There are a few numerical issues worth highlighting. Finite domain size and boundary reflections can alter long-lived solutions. Increasing the domain or adding absorbing damping boundary conditions reduces that problem. Discrete peak detection that are used at grid points produces a bit of jitter, and a quadratic subgrid refinement would help. And there we have it. Thank you, and this ends my presentation. The code and the figures used are available within the project and can be found on the project PDF.